So it is my great pleasure to introduce you this evening's keynote speaker. He is very well known to the community of X-ray absorption spectroscopy, Dr. Vittal Yachandra. Dr. Yachandra received his bachelor degree from Loyola College, University of Madras, India in 1973, and a master's degree from the Indian Institute of Technology, Kanpur, India in 1975. He then moved to the United States and received a master's degree in chemistry from University of Chicago in 1977 and a PhD in chemistry from Princeton University in 1982, where he used resonance Raman spectroscopy to study iron-sulfur proteins with Thomas Spiro. He then moved to Lawrence Berkeley National Lab as a postdoctoral fellow with Melvin Klein and Kenneth Sauer to study zinc and cobalt carbonic anhydrides using X-ray absorption spectroscopy. Since 1985, he has been a senior scientist at the Lawrence Berkeley National Lab in the Physical Biosciences Division. Dr. Yachandra's main research interest has been focused on the study of photosynthetic water oxidation and the structure and mechanism of the manganese-4 calcium cluster, oxygen evolving complex, by X-ray absorption, electron paramagnetic resonance, and vibrational spectroscopy. His other research interests include the application of X-ray absorption spectroscopy to low-Z elements like sulfur and chlorine, especially ligand K-edge spectroscopy of sulfur in ferredoxin and related molecules to understand structural correlations with redox potentials. He has more than 160 publications, many of which have been in Nature, Science, PNAS, and JACS. His H index is 60, and the title of his lecture today is Taking Snapshots of Photosynthetic Water Oxidation with an X-ray Laser. Dr. Yachandra.
Thank you, Farida, for your kind introduction. And I would like to say it's a real pleasure to be in Hyderabad for me. It feels like home. I'm very familiar with the language, so I'm very comfortable. And I would like to thank Professor Gautam Desiraju and the organizing committee for inviting me to talk about our work. Our work is about the photosynthetic water oxidation, the structure of the catalyst and the mechanism. This work is done in collaboration with my colleague, long time, Junko Yano. So all the work I'll be talking about today is in collaboration with her. So she could be giving this talk as well as I. The first thing is I would like to tell you is about photosynthetic water oxidation. And I would like to start with one of my favorite slides. The favorite slide involves evolution of oxygenic photosynthesis. It's an extremely interesting thing that we all take oxygen for granted. But actually, when life started in the very early Earth, there was no oxygen either in the sea or in the atmosphere. It was a completely reducing atmosphere. And it was mostly anoxygenic life forms, primitive life forms, which were in aquatic situations. And somewhere along the line, photosynthesis was occurring, but it was anoxygenic. Some bug, the cyanobacteria, figured out how to use water as a source of fuel. Fuel means being able to extract electrons from the molecule. So it oxidized water. The byproduct was oxygen, and oxygen in a way is the first pollutant of our Earth. It collected slowly in the seas. You see, this is a log scale. And it took a heck of a long time before it got to the point where it exhausted all the iron in the oceans. And this is the famous banded ion formations. And after about 1 billion years of this process, oxygen started escaping into the atmosphere. And this is the oxygen which all of us depend on, and all life forms as we know it depends on. So this reaction is an extremely important reaction, splitting of water to oxygen, which is so simple but so important. And I'd like to also say that it is this oxygen which created the ozone layer, which made what you call a filter for UV, and terrestrial life evolved. And then respiration evolved. And more complex forms of life were able to thrive because of oxygenic respiration. And you had eukaryotes, you had all kinds of things, and then there's a Cambrian explosion, and then now it is 20% oxygen. And it's also, there's a downside to it. It's the same oxygen which created these huge fossil fuel reserves, because those are trees and things which grew and in plentiful quantities became the fossil fuel. So the oxygen which created this life also has created this fossil fuel which we are burning, which could lead to a different scenario in the future. So that I would like, that's the reason I'd like to start with it. And these are the two, the fossils of real cyanobacteria from 3 billion years ago almost, and the present day cyanobacteria, they are very similar. Nothing much has changed in their life, the way of life. Okay, let's go through the introduction of photosynthesis. We all know, we have learned it in high school. Photosynthesis consists of carbon dioxide and water. You throw in light and you get carbohydrates and oxygen. That is a simple reaction you hear about. And it's of course in all green plants and algae and cyanobacteria, and it is in the thylakoid membranes. It is a membrane-bound complex, the whole photosynthetic system. And I'll go through them quickly. Photosystem 1 is where the electrons go into the NADP, it makes NADPH, which goes into the Calvin cycle. And there's a whole series of chain through the cytochrome B6F complex, and there's photosystem 2. Photosystem 2 is where water is oxidized to oxygen. This is a very simple reaction. The reaction consists of 2 water molecules and 1 oxygen coming off. There's 4 photons. And this entire reaction is catalyzed by a manganese-calcium complex, 4 manganese and 1 calcium. Let's go through this in a little bit more detail, the photosystem 2 complex. How does it do this? It has a reaction center, a photosynthetic reaction center. It absorbs light and creates the charge separation. The charge is stabilized by going through the quinone acceptor pool, which feeds the entire chain of photosynthesis and life eventually. And the hole created in P680 has to be filled, and through a tyrosine residue, there is an oxygen evolving complex. So every photon this reaction center absorbs and creates a hole. 1 electron is extracted from the oxygen evolving complex. And this oxygen evolving complex is where the catalyst is found, the manganese calcium catalyst. So you extract 4 electrons and you release 1 molecule of oxygen, and there are 4 photons absorbed. This is a very interesting reaction. You have 1 electron photochemistry coupled to 4 electron redox chemistry. And it's complicated because these 4 redox equivalents have to be stored somewhere. And that's what this calcium manganese cluster does. It's kind of unusual. 4 charges in a protein is a lot. The electrostatic potential is quite a bit. So it kind of charges up like a capacitor, and in almost one fell swoop releases the potential and releases oxygen. And it's very logical. You have 4 photons, 4 electrons are coming out, so there are probably 4 intermediate states. So for a chemist like us, is a fabulous thing to be able to study these intermediate states, figure out what the structure is, what is this mechanism, and there are some very interesting things about the mechanism, which I'll tell you about. Let's go through this thing in a little bit more detail. The dark state, if you take a photosystem 2 preparation and leave it in the dark, you get the S1 state. These subscripts refer to the number of electrons pulled out. Think about it that way, or oxidation equivalent stored. Then you give it one flash of light, you get S2, second flash of S3, and then these states are all, can be made and frozen. This one, S3 to S0, where oxygen comes off, cannot be done in a frozen way. It only can be done at room temperature. It becomes important about why I'm telling you this. Anyway, this is a seminal experiment from the 70s where they took photosystem 2, flashed it with light, and saw oxygen evolution coming off with a periodicity of 4. So a kinetic model was developed with 4 states. And these 4 states are real chemical entities. So it becomes fun. Why is the reaction also interesting from other points of view, from the society point of view? I would like to show you one slide for that. This is a slide which is from Dan Nocera at Harvard. Initially he was at MIT when he made this slide. If you take the thermodynamics of water oxidation, 2 water molecules to 2 molecules of hydrogen and oxygen is 237 kilojoules per mole. That's about 13 million joules per liter. So his calculation was, let's take a Olympic-sized pool, which has 3.2 million liters. And what you get is 42.7 terawatts. That is a lot of energy, and a third of the water in the pool, split every second, can provide all the power the world uses presently, which is about 13 terawatts. So you can imagine the potential of this reaction. So it is, and that is the reason why you cannot open a chemistry journal these days without seeing an article on water splitting. There is some catalyst all the way from every metal you can think of splits water, and they're trying to figure it out, but it's not that easy. We have to learn from nature. And how do we, okay, this is what it means. Water plus light does indeed equal oil and coal. Why is it difficult? I already told you about the 1 electron coupling to the 4 electron. And this is an awfully dull slide. Sorry about that. And I don't know what's going on there, but over here, the point I would like to make is, this is in aqueous solution. This is nature. Nature has figured out to take each of these steps and kind of divide it into 1 volt each. So you can actually use red light to advance each step, which is what photosynthesis largely does. It absorbs red light. That's why plants are green. And on the left-hand side, you see that in order to accomplish this reaction, you will actually need UV light. Water, hydroxide, peroxide, superoxide, and then oxygen. And the catalyst and nature's catalyst does it in a really elegant form. And there are 3 points which I would like to go through quickly, is that it does it in the last step, either in a 4 electron or a 2 plus 2 electron, with some intermediate state between S3 and S0, the last stage. And it also decouples, decoupling of proton and oxygen release. The protons are 1, 0, 1, 2. You have to remove 4 protons along with 4 electrons, and oxygen only comes off at the 4th one. And that is remarkable too. It's not in complete sync. And then it's coupling of electron-photon transport. So all this thing, it orchestrates in a very, very elegant fashion at room temperature in ambient pressure, while if you want to do the reaction with an artificial catalyst, it's not that easy. Okay. I already told you about this thing. It's a very elegantly arranged, thermodynamically elegantly arranged. There is some activation energy, but it is very close to thermodynamic potential, which means you waste very little energy. If you try to do it artificially, you waste a lot of energy, which is called overpotential. It's a huge overpotential, which is basically not efficient. Nature does it with almost 0 overpotential. And S1, S2, and S3 states, as I told you, can be made and frozen. The last step, which is this step in blue here, is a step which you cannot freeze. You have to do it at room temperature. And it gets important. As in the middle of it is a crystal structure, which will come in a second. The important questions we are addressing are, how does the OH bond form? Because the formation of the OH bond is the most critical part of the reaction. Once overbond is formed, a peroxide bond, any metal can oxidize peroxide to oxygen. Ferric ion can oxidize it. So that's the reason if you put your finger in a peroxide bottle, you get bubbles. So you don't need you don't need another extra energy that way. It's kind of downhill. And the evolution of molecular oxygen, of course, occurs here. Substrate binding, because it has to go through the cycle, it is a really, really efficient one. 3,000 molecules a second. And right now, I think the artificial ones are probably 2 to 3 orders of magnitude slower. And the reorganization of the manganese cluster, how does it change these redox potentials and make it the way it does? That is the electronic structure. So we are interested in both. And this is a slide which just kind of summarizes 30 years of data, but I want to show it because an enormous amount of spectroscopic evaluation has gone on over the last 3-4 decades to arrive at where we are right now, along with crystal structures, which is the topic of our conference here. And to summarize, there is a very good XAF structure, the manganese XAF structure of the S1, S2, S3, S0. These are the stable states. You can make them. Give them a flash, freeze it, go to the synchrotron, collect the data at extremely low dose. And that becomes apparent in a second. And there are models developed based on comparison to inorganic complexes. There are very, very accurate distances, which is what XAFs is known for. Metal-metal distances, metal-ligand distances, and along with XAFs of polarized XAFs using crystals, we had a pretty good idea of what the structure was, what the distances are, what the vectors are, and therefore what the structure should be. It is an intellectual exercise on how you do this, how you come up with a model with these parameters. But it was not the crystal structure. We did not have a real structure. And that limited how do you go beyond just, how do you figure out how does this system work? Well, there were many crystal structures before that, and we'll see why there was a problem with them. In 2011, there's a real cataclysmic change in our field when this crystal structure came out from our Japanese colleagues. And at 1.9 angstrom, a beautiful structure detailed here, and quickly going to the crux of the matter, as they say, is the manganese complex. They had a structure of the manganese complex in great detail with all the ligands, 4 waters, 5 oxygen bridges. For us, when we were doing spectroscopy, this is gratifying because it is very similar to what we were proposing or others were proposing, but not exactly the same. Okay. This was a spectroscopic model, modified with some input from crystallography. See, there is no bond here. It is very important. And very interestingly, very accurate distances. And this was the data from the 2011 paper at synchrotron radiation, 100 Kelvin. And they are somewhat longer, the distances. And everybody knows that X-rays do damage things, and it is pretty clear that it is probably caused by X-ray damage. And this is another very important paper from my colleague, Junko Yano, in 2006, where systematically she studied the radiation damage of solutions of PS2 and crystals of PS2 at different temperatures. And this is at 10 megagrays. The Henderson limit and the Garman limits are at about 20, 30 megagrays, and they are wonderful markers for overall crystal structure. But in this case, you see at that dose, even at 10 megagrays, this is the damage axis, most of it is damaged. The reasoning was that manganese 2 is what is produced when the complex is damaged, because the complex is a high valent complex, manganese 3 and manganese 4s. So it is mostly damaged by about 10 megagrays. And in addition to that, the XAF spectra are pretty dramatic. It does tell you it is not just reduced, it has fallen apart. It has fallen apart quite interestingly. See, this is the canonical X-ray spectrum of an intact PS2. When I say it's intact, it's because we know it's intact by following the dose we give it, following the Zane spectrum of manganese, following the X-rays, and it is about 0.01 megagrays of dose. So that is the kind of dose we use for X-ray spectroscopy. And even this is now at, you see all of it is completely different, even at 70% of this, the X-ray spectrum. And this is colored in green because 25% here. That is the 2011 paper. So even at that dose, there is some amount of damage. So you see the spectrum, the X-ray spectrum different. That's why the distances are longer. And maybe there is some difference in the interpretation of the structure. And maybe that is why one of the bonds is not there in the spectroscopic model. Well, I think it's pretty obvious that it is very hard to do really good, detailed, more complicated spectroscopy or crystallography using X-rays at room temperature, because many of the things I showed you are at cryogenic, all of them I showed you are at cryogenic temperature. So if you have to go to room temperature, which is really important for the last step, where the OR bond is formed, then you need to go to a different way of doing it. Fortunately for us, in 2011, there was this fabulous machine. The XFAL came into being, and the advent of this instrument has made some of these experiments possible. And what is the difference between a synchrotron radiation and an XFAL radiation? I think most of you probably know what it is. I'll so quickly go through it. In synchrotron radiation, you put out nanojoules with nanosecond spacing, and there are a whole bunch of them. So in 1 second, there is a certain amount of flux, let us say. What the XFAL does is it compresses most of it into a 5 to 300 femtosecond pulse. So in a few femtoseconds, you have as many photons as what you had in a second in synchrotron radiation. And that's interesting, and that is very, very useful. But is it really useful to collect spectroscopy or crystallography? Is it useful for that? And a fantastically important paper by Noitza and co-workers, a pioneering group here, which showed that within this pulse width, the proteins do survive. So you can actually collect data before you destroy it. So it's now the buzzword, collect before destroy, is what XFALs are great for. And that makes all kinds of things possible, because reactions which go on in room temperature can be followed in real time. So our approach was that we would use the X-ray free electron laser to study the manganese calcium complex and the photosystem 2 overall protein. We would use X-ray spectroscopy to look at the manganese calcium cluster, because I told you why electronic spectroscopy is really, electronic spectra are important to understand the modulation of the redox potentials and therefore the mechanism of the reaction. And then the overall structure of PS2, photosystem 2, to look at the side chain motions, the quinone sites, and the geometry changes. You need both. You need the geometric structure, and you should never be satisfied with just that. You need to know more about it. You need to know spectroscopy to combine it, and how does nature make these reactions possible. And we decided in the very outset that we would combine both of them. And this is a very critical thing. It made life miserable, but it really was important, because it gives you confidence in the quality of the data you get from crystallography. Okay, the questions which we were addressing largely relates to how this bond, what we are addressing right now, is how does this OR bond formation occur? I'll go through these 3 questions quickly. How? They are divided into 3 basic categories, where in one case, these 4 charges all accumulate on one manganese atom. and then it becomes extremely electrophilic. So there's nucleophilic attack on an electrophile and an overbond form. This is a mechanism which is well known in inorganic chemistry and well liked by inorganic chemists. The other extreme is an oxo-oxyl. This is just a nomenclature for delocalized charge. The charge is delocalized over many manganese atoms or even over the ligand, which is oxygen in this case, and then that forms the overbond. This is particularly interesting for people who are studying proteins because they don't like charges in one place. And in the middle there is a kind of a halfway house, acid-base mechanism, and which is also very, very viable. We need to figure out which one of it is. In fact, we still don't know which it is after all these years of research. And then, where does it occur? There are 4 terminal oxygen ligands and 5 oxygen bridging ligands. You can take your pick. You can make the bond between various combinations of them, or you can introduce an exogenous oxygen, a 6th one, and create a bond. And these things summarize all 6 of them. We'll go through them in the next 30 minutes or so and eliminate some of them as probably not likely. I'm being very careful with the words because this is an ongoing research. Nothing is completely conclusive yet. And the last one, when? Does it occur here, or does it occur here, or does it occur here? The overbond formation, that is. And we will get to that also. We'll go through each one of them in this later part of this part of the talk. Okay, so we went about setting up our experiment. We decided to make our own thing for this one particular protein. That is the way it made it, we couldn't adapt things that easily. So we came up with something which is unique for this system. Some of it, of course, is borrowed, but we'll see some of the problems that it creates. We used a sample injector initially, which was developed by some of the pioneers in XFEL research. And you have a train of X-ray pulses coming in, intersecting the crystals flowing down, and downstream you collect the diffraction pattern. That is the standard, so-called standard method 4 years ago, 5 years ago. 90 degrees to it, we decided to set up an X-ray spectrometer, an emission spectrometer. You can use the same energy which you use for collecting crystallography to excite the manganese atom and collect the emission spectrum. The emission spectrum we designed along with a collaborator, Uwe Bergman, a dispersive spectrometer, which means in one shot you get the full spread of energies and you get the full spectrum. And in some cases you can get it in a few minutes. In PS2 it takes about an hour maybe, or 20 minutes, or depending on how good things are. So in the same experiment you do both crystallography and spectroscopy, and one complements the other. And why, we'll go through why we do emission spectroscopy in a second. And it's pretty exciting on the X-ray beamlines, on the XFEL beamlines. You get these shots, you see these diffraction patterns, and it is quite a thrill. You see it happening as you are there. And after a while, of course, analysis starts and you start saying that this is not good enough and all the other problems start. But science in real life, this thing, seeing it is pretty exciting. And the emission spectroscopy, the complementary method, what do you get from that? Here you excite the 1s electron into the continuum. You look at the emission from any level you want to by tuning your spectrometer to that energy. You can look at it from 2p to 1s, 3p to 1s, or the valence to 1s. These are the 3 different spectra. The sensitivities, this is easiest, this is the middle, easy, this is really hard. And each one of them has different kinds of information. This is oxidation state, this is oxidation and spin state, and this is ligands, about the ligands, electronic structure of the ligands. So this is ideal to look at the electronic structure. We decided to use K-beta 1,3, which is a good marker for oxidation state. We knew that oxidation states would tell us which part of the cycle we are in. It would tell us about the quality of our sample. Is it destroyed, not destroyed, reduced, not reduced? And it gives us in situ monitoring of our sample. Okay. I already showed you that the pioneering work by Neutze and co-workers, where they showed you can collect diffraction before the crystal is destroyed. But there were questions about spectroscopy. Is it possible to do spectroscopy because is the metal reacting to the intense pulse of X-rays differently? And is it still there? Is it in the form which is viable? So these are small baby steps, but these are important steps. We knew that it was diffusion of X-ray generated radicals not a problem because that is 20 picosecond time scale and the pulse width was only at 100 femtoseconds or smaller. So some initial data on inorganic complexes which showed that this is a high valent manganese complex, this is a low valent manganese complex, and the dotted lines are data from synchrotron. They are right on. There is no problem. You can use synchrotron, X-felt pulses to collect the same spectra. And we did this on PS2. This is synchrotron radiation at 8 Kelvin, where you don't damage this sample. This is X-felt. They are right on top of each other, green and black, while at room temperature in the synchrotron radiation, it is quite damaged. That is manganese 2. The third one, crystals and solutions are pretty much the same. So this made the experiment possible. It was a proof of principle, but necessary. Our first try, our first publication, the electron density for PS2 in the dark S1 state at room temperature. So this is pretty much the first room temperature structure of photosystem 2. And we were able to see that it's very close to what the synchrotron density was. And we were able to see density for the manganese complex. And the bad part was, look at this number, the 6.5 angstroms. So again, a small baby step. We could do a room temperature structure of this 500 kilodalton protein, and the manganese complex can be seen, and it is intact. Can we go around the cycle? When I showed you the setup, I did not tell you about one part of it. We built in a visible laser illumination system, which very often in most experiments is one flash. Here we had 3 lasers in the beam, in the capillary, and 1 outside. So you could go to all the S states by picking on the right sequence and on the right delays. The delays are really, really important. You have to wait half a second before you get the second flash and the third flash to advance the system. Because the system needs to, the acceptor side needs to open up in order for it to get to the next step. Even though each step is fast, the acceptor side is the roadblock. It's a little tricky, but you need to wait quite a bit of time if you want to get turnover. So, and the fourth laser, you can get much shorter delta T's if you wish. And that becomes important in the last step. Because there the times are, you need data from smaller steps. So we tested this thing, this methodology, and happy to report again that going through the S states and also the last step, a time point, we could see manganese density quite clearly. This is S1, S3, between S3 and S0. And we were able to see the anomalous diffraction too, where here you see the calcium is excluded from the density. And happily, we were able to see that it is turning over quite clearly using the XES, in situ XES. This is a reduction, which means The most oxidized state is getting to the reduced state when it goes through one cycle. That is this one. And this is in between where it's actually getting oxidized. So in a way, we proved that it is possible. And again, you see these numbers. They are around 5 angstroms. Another small baby step. Okay. There clearly are challenges for XFEL experiments. And each experiment, depending on the system, has different challenges. And they need to be addressed one step at a time to optimize it to make sure that it is compatible with your system. And in this case, there are three challenges which we identified. One of them is that there is a large heterogeneity in the crystals. This is a real video. This is big, small, tiny, whatever. The second one was, of course, the analysis methodology. It is being developed as we speak. Every day, things are changing. And we are fortunate to have an extremely good collaborator, excellent collaborator, Nick Sauter, who is actually our neighbor in LBL, and the Phoenix group is the other neighbor. So putting these two things together, they have come up with their own way of analyzing the data, and very successfully. And for some of you who may not think about XFEL data all the time, you don't get data from the full rotation angle. You only get it from a slice on the sphere, evolved sphere. So the full intensities are not there on your spots here. So depending on where you are, you get different intensity, and that creates a problem in the analysis. And this group has its own way, along with collaboration with Axel Brunger's group, and with post-refinement methodology, they have been able to do an extremely successful job in analyzing the data. I will not go into those details. The third one is a physical limitation in some of the ways we were doing the experiment. We were not using the beam time ideally. The rate was really, really poor. So we had to do a better job. So if you had crystals like this, it was not really good. You had seeded crystals. We have got fantastic resolution now. We're going up to 2 angstroms or better. And you can see that we can really reproducibly make these very uniform sized crystals. And we came up with a new method for introducing the sample. We used an acoustic droplet ejection. You'll hear more about it from my colleague Jinko, Jan Kern, and Alan Orwell. And we deposited them on a tape with Mohs and used very precise illumination, so there is no doubts about it. You're illuminating the dot, and then you're blasting it with an X-ray laser. So our turnover is much better, our indexing rate is much better, and we do the same experiment with, both XES and XRD. And a little cartoon here just to illustrate if it works. Yeah, there it is. This is the stream, this is the droplet method, and you have the 3 visible lasers hitting them at precisely well-defined delta T's, and the X-ray laser then hits the drop. And you collect both crystallography, spectroscopy and crystallography can be done. And this has made life a lot better for us. I would just like to point out that, of course, instrumentation is a lot more complicated than what I just showed you in the cartoon. And this number, it's really dramatic. It made life, it made many of the experiments we are doing right now possible. We actually collect data most of the time rather than rarely. And you can actually plan an experiment. And just to show you, this is, again, I hope it works. This is the diffraction pattern. This is not PS2, this is another protein. This is so clear, I just picked this. You see the diffraction pattern. This is in real time. Of course, you're only picking one every 10 seconds here. This is the drops being blown apart, and this is the XES spectrum, and this is the XFEL parameters. So all 3 are happening, and you can immediately evaluate the quality of the data and change your conditions. on site. Okay, the next 20 minutes I have, 22 minutes I have, let me tell you about how we use these new methods of analysis, sample introduction, and illumination, and what are the data we have got, and all at room temperature. This is the room temperature structure at about 2.3 angstroms or so now, and you see that the protein is expanded laterally. It's not in the membrane plane, it is expanded. All the helices, the blue and the gray don't match. One of them is room temperature, one of them is the cryogenic temperature from the Japanese group. If you look at the cofactors, where the real stuff happens, they have also gone farther apart in the plane of the membrane. This is by how much the colors mean. On average, about 0.4 of an angstrom. If you think about electron transfer between these cofactors, 0.4 angstrom is a mile, because it can change the rates by 25%, which means photosynthesis slows down by 25%. At room temperature, it is slower, because they are farther apart. And we need to test this at other reaction centers, or it's only in PS2 with this particular packing. We need to see that if it's a general thing or just in this particular case. And there are residues in this region and this region, which are outside, where there are clear differences between room temperature and cryogenic temperature data. And the kind of things we see, for example, you pick this residue, is that there are two rotamers, which is only possible in the room temperature, but not at cryogenic temperatures. So in real life, things are wobbling around, and probably some of them are crystallized in this side, some of them on this side. Same thing you see here. So this is again expected, but it's kind of nice to see that. The next step was, of course, there's the dark state I just showed you, was to look at the S-state advancement as a function of the flash number. This is the dark state, and you see this pretty nice resolution. These are the terminal water oxygens. You can clearly see the two of them on this oxygen, and you can see two of them on calcium. Those are the four. And many of the bridging oxygens, it's very difficult to see, because there's so many electrons in the metals right next to it. But it is quite clear that the terminal oxygens are there. And that is the dark state. Let's flash it once. You get the first flash and the second flash. This is the three states. And I'm going back. Things are happening. I'm not going to go into the details. I'm just trying to, I'll present an overview. And my colleagues, Jinko and Jan, who have talks tomorrow and day after, they'll present some more aspects of it in detail. And there are motions in the oxygen atoms and the metal atoms and some of the residues in the neighborhood. Once we started seeing things more clearly, it became imperative that we make absolutely sure that we do have turnover and we have a quantitative idea of how much it is. So that's what this slide is about. And one of the things we did was we built a facsimile of the same system or similar system as much as possible in a collaborator in Uppsala, and he did oxygen evolution measurements using mass spectrometry. And they perfectly turn over with the conditions we use by oxygen evolution. That is the perfect marker. Oxygen evolution is a gold standard. And then the in situ method, XCS, of all the flash states, that is 0 to 1. You see there is a change in the spectrum. Second flash, there is a change in the spectrum again. Third flash, it's not too obvious in this thing, but when you do a careful analysis of the first movements, you see the first movements are clearly going down in energy, going up, and that is a marker of oxidation and reduction, which is what you expect. You get oxidized up to here, and then it gets reduced when it goes to the state again from here to here. So oxidized, reduced. And now you can get a number on this thing. And our estimate is that it is about 60%, the lowest number. It's probably bigger, better than that, of turnover, especially in this state, which is one of the more important states for this particular talk. Okay, another experiment, another data analysis point which shows that we're getting turnover. Remember, the quinones are accepting electrons, so they are changing structure a little bit. And that's what I'm going to show you now. This is the first flash. This is a difference map. You see that the quinone is clearly moving, QB, and this is what you expect. In the 2 flash to 0 flash, here to here, from S1 to S3, there is no motion. It's almost back to where it was, which is what you expect. It is a 2-electron gate, the quinone. And then the next step, there's again motion. So it is actually now going back here. So we see the full cycle. So it is moving the way it is supposed to do. So it's good to have, it's important to have these kinds of controls. Otherwise, you'll be creating states and interrogating them with X-rays without knowing what you're looking at. It is important to have an independent tool. In situ would be best, but ex situ, if it is in the same conditions. With ex situ is in completely different conditions or different kind of setups. Be careful. That's what we think. Okay, what is the summary of this particular S1, S2, S3 at about 2.25 angstroms? There are lots of things moving around, I showed you, and you can see the things pointed out here. I will not go into each one of them, but as I said, my colleagues will talk about it. And one of the more critical things is that we do not see an oxygen between O5 and manganese 1. This is the density in the dark state. And here, sorry, this is the position where we're looking for the sixth oxygen to come in. Remember, I showed you the mechanisms. There were mechanisms where a sixth oxygen comes in. That's a very popular mechanism for various reasons. Where it comes in is not clear, which state it comes in. One of the suggestions is that it comes in, or proposals, it comes in the S3 state. And we do not see any density there, at least in the 2F4 minus FCs. And this led us to believe that of the 6 mechanisms I showed you, this mechanism where there is an insertion here, and this one, which is the favorite of most people, insertion between these two, is less likely, at least in the S3 state. Okay? We do not know what is happening post S3. That is a different story. But in the S3 state, it's not probably likely. Okay. I want to just show you. This is the same time we published a paper about 4 months ago. This is another paper from the group in Japan, which published a paper on the S3 state, which said that they were seeing density between O5 and manganese 1, O6, and they proposed a peroxide bond formation in the S3 state, because the distance was something like 1.5 angstroms, which is a peroxide bond. And this was based on isomorphous difference map. Isomorphous difference maps, I don't need to tell all of you or experts on this, need to be done very, very carefully. And we are happy to report our data sees the same kind of isomorphous difference maps as what they report. So both groups do see the same kind of differences, but we do not think that this is another oxygen 6, a new oxygen coming in. We interpret this differently, and I'll tell you what we interpret it as. There are also independent reasons to not support a peroxide bond in the S3. There is a wealth of information, spectroscopic information, on the S3 state, which says it is the most oxidized state. When a peroxide bond is formed, you have to reduce the manganese complex by 2 electrons. You cannot have a peroxide bond with all manganese oxidized, or it being the most. It is a basic inorganic principle. You cannot. You have to reduce it. And we know S3 is the most oxidized state, that it is not reduced by 2. I cannot stress this enough. So we need to use other methods. These conflicting results are probably because it is very hard to determine density at the bridging positions. That's our conclusion. And I will just now show you some of the more recent work, which is not published. This is the one I just showed you. This is the place where the O6, if it is there, occurs. As you can see, you do not see it in the 2F4 minus F6. We were able to collect data now at about 2 angstroms, and these are the maps where we see the oxygen and the manganese atoms in the dark state. One is the 2F4 minus Fc, one is the oxygen omit. You can see all 4 terminal oxygens, W1, W2, W3, W4, and the 5 bridging oxygens, and of course the 5 metals. And when we go to the S3 state, the 2 flash state, I'll go back and forth, we do not see any extra oxygen density there where it is supposed to be. All we see is manganese moving and O5 moving and all kinds of, all kinds of things moving. Like for example, manganese does move. I'm sorry, I'm doing this wrong. So this manganese moving and this oxygen 5 moving and some small motions in the rest of it are happening, but we do not see an O6 insertion. And so we think that it is the motion of these other atoms which creates the isomorphous difference of that density, because this is the same isomorphous difference. Thank you. Okay. And, so maybe what we say about the unlikelihood of those 2 mechanisms is okay. Can we do more than that? So what we decided to do was we also wanted to try using ammonia, which is an analog of water. It's an interesting thing in photosynthetic systems. Ammonia can bind to the manganese complex. That's been shown by spectroscopy. It's been shown by EPR, it's been shown by XAPS, and it is also known that it binds to manganese, but at the same time you can evolve oxygen. It creates an interesting situation, which means where it binds or which water it displaces is not the water involved in the overbond formation. So it gives us a clue on how to exclude more mechanisms. And the data, when we did treat a sample with ammonia, we see changes in the W2 site, but not in the W1 site as much. So is this an indication that actually it binds in the W2 site? We don't know, because water and ammonia are the same in terms of crystallography. But this is intriguing, that it does seem to perturb this site more than this site. Is this perturbation indirect? I have no clue. It's impossible to say. But if it is a direct perturbation, then it's likely it is W2. In which case, remember I said this is less likely, this is less likely. Now these 2 become less likely because they involve W2. What is left are these 2, at least out of these 6, which seem to be the more talked about one. And I'll leave it at that. I'm not going to say what it is or what it is not more than that. But the approach is eliminate possibilities and see where we are going. And with better data, with more time points, beyond S3 is what is necessary. So this is the isomorphous difference of the high quality data now from S1 to S2, S2 to S3, and we are proceeding into the time zone here now, the last step. And it's an exciting stage right now where probably things will start coming together, and we need to be careful as we go forward, eliminating possibilities and see where it is converging. And the last couple of minutes I have, I'm almost right on time. I would like to show you a couple of slides which tell you a little bit about how interestingly exciting these experiments could be. This is the control room of one of the beamlines in LCLS. This is Jinko sitting in the captain's chair here, Jan running the beamline along with the beamline scientists. Diffraction patterns are coming. Here you see only water rings, and here the droplets are getting blasted. You can monitor that. The XCS is coming here, and there's a whole bunch of activity with a whole bunch of people. So it does take a lot of people working together, and this maybe is an exciting diffraction Athena is seeing, and this is the crystallography beam station. So all of them working together, talking to each other, and coordinating and optimizing is essential for this experiment to work. And we have a large collaborations. This is our group here. I already mentioned Jinko, who is co-leader of this project. Jan, who is a very key person, and postdocs and graduate students. Nick Sauter and Paul Adams' group, they are absolutely critical. I mean, everybody is critical, but they are critical for the analysis. Messinger's group for the oxygen evolution. Alan for the sample delivery system development. He's been extremely helpful to us. The SLAC, LCLS, and all the other people. And there are more people here from other beamlines. And I didn't say much about the soft X-ray, but we are involved in those experiments also, and SACLA, including SACLA. And finally, our support is largely from the DOE and NIH, which is not here, and the beamlines are all mentioned here. And I'd like to show a beautiful sunset on our lab. Not usual, but this is how it is. And my final slide, this book just came out last week, X-ray free electron lasers by the Royal Society of Chemistry. It's edited by Uwe Bergman, whom many of you know, and myself and Jinko. And many of you in the audience probably contributed to it. Thank you. And it's a very nice book about various techniques and how the X-fields are being used in materials, chemistry, and biology. I thank you for your attention, and I'll be happy to answer questions.
John Helliwell, University of Manchester in UK. Just to congratulate you and all your colleagues in really doing a very fine suite of studies. The signal from the sample opportunity to optimize what you're trying to find out occurred to me that in the aquatic photosynthesis situation where the light levels are low might accentuate the structural detail and might be therefore more amenable to the structural approach, be it crystallography or XAFs, or indeed the other spectroscopies that you talked about. So my question is to do with, do you think there are opportunities of optimizing the choice of sample, and in particular to take photosynthesis from the low light levels in the ocean as a possibility?
That's a hard question to answer.
You don't need to answer it now. It's a thought. Thank you very much.
It's an interesting thought.
Next question.
Hi, I'm Alex Guo from Carnegie Mellon University. I have one question, two. One is whether you think S4 is really intermediate or is more like a transition state.
See, when I mentioned about the redox potentials and how the last step occurs, I mentioned it can be one 4-step mechanism or a 2+2 mechanism. If it is a 2+2 occurring in the last step, there is actually an S4 state. Okay? If it is not, it is just a transient state. It's not it's either, is there a dip in the potential energy diagram or not is the question.
Yeah.
If there's a dip, there is an intermediate state, otherwise there's a transient state. We don't know that unless we do all the time points. And we are very excited about what is forthcoming from those data. So it's a question which has been in the field forever. Other spectroscopies have identified some kind of an inflection in around 150 microseconds, but nobody has clearly said that there is an intermediate state. Okay? So that is the best I can do in answering that question.
And another one probably also is hard to answer, is that you think the mechanism is more involving manganese 4 oxyl radical state to do O bond formation, or is iron 5, oh sorry, not iron, manganese 5 oxyl?
I didn't see, we have a completely different project with soft X-ray spectroscopy and also hard X-ray spectroscopy, directly addressing the electronic structure much, much more deeply. And those things will probably answer this question. And there are experiments underway, especially soft X-ray experiments, which would probably pick up manganese 5 more easily than hard X-ray. But hard X-ray emission spectroscopy could do that, and we are pursuing all those avenues. So at this time, it's still ongoing. We do not know manganese 5 is involved or not.
Okay, thank you.
Thank you. Next question.
First of all, thank you for the update on photosynthesis. It's really exciting to see what can be done with X-ray lasers. My question is concerning the pump-probe approach, because when we excite crystals, we typically only get an excitation level of between 10 and 30% with a single flash. If you now have 3 or even 4 flashes in a row, and each one is 30%, 30%, 30%, how do you know that at the end you don't get a mixture of 2, 3, 4 times, 1 times excited states inside the crystal?
Very good question, because in our field in photosystem 2, the concentration of the samples and the amount of light needed to saturate the samples have been well quantified using oxygen evolution and EPR, which we do both of them. Oxygen evolution in collaboration and EPR by ourselves. And what is called saturating is, for all practical purposes, 100%. The reason this oxygen evolution and the concurrent EPR signal, which shows oscillations go out of phase, is there is an intrinsic miss which is intrinsic to the system, not to the laser illumination. So we reach the point, we use the amount of power to saturate it and get as close to the intrinsic limit. In this case, it is 10% misses. Okay, that is probably the largest parameter, largest number you can put on it. It may be smaller. So it is not 30% or 40%. It's more like 10% or even smaller in photosynthetic, in photosystem 2. So we use crystals and the power of the laser to match it, to saturate it perfectly. Otherwise, what you said would happen.
Thank you.
Thank you. Any other question?
Hello?
Yeah.
Robert Feidenhansel from the European X-FEL. I was very intrigued by this wonderful talk, and particularly by the last slide you showed, because we are now opening a new facility basically next week in Hamburg. And the complexity of experiments, I think that you showed you, where you showed this small movie of people in the control room, is also a little bit scaring. So how do you see the opportunities for new groups entering which don't have the experience yet?
If depending on the systems you're studying, suppose you want to get the crystal structure of an extremely difficult protein and you have a certain limited amount of sample, then the best thing would be to collaborate with a group which knows how to do it and not try to, and also groups which know how to do it should make these things available. In fact, now it is common practice in the United States for granting agencies to make sure the resources for our tape drive, for our emission spectrometer, the emission spectrometer is available to anybody in LCLS. We designed it and built it from our grant money, but it is available to our competitors. In fact, they use it. Okay? And the same thing is true of the tape drive. It will be available, and the CAD diagrams are available on the journal web pages. Anybody can build one. In fact, people are building it. So these are built-in mechanisms to make it an open resource, which is the way it should be. But to do an experiment like what we do, I think it's very hard for, unless you're in it and you develop it, it's not that easy. But not all experiments are this kind. So there are different varieties. So I would say one needs to evaluate each one carefully and make sure that as a director, you will be faced with this, I'm sure. And I'm not the person to advise you on that. But I've used the beamlines a lot. And our beamlines are all specialized experiments which need a lot of people. And when I heard that some places in the European XFEL, there are only 5 people in the control room, it sends shivers through me.
Thank you so much. Please join me to thank Vittal once again.
Thank you very much. On behalf of the organizers, it's a real pleasure to present a small token of appreciation to the speaker, Professor Yachandra. Thank you very much. One more minute. Professor Farideh Jalil for this chairing this session. Thank you very much. Thank you very much.